question just because they flip the typical relationship between the variables. So usually it's that it's a function of time and it gives you amount of some catalyst. But here it's a function of the amount that you have of this catalyst, they're calling it, which is measured in milliliters, gives you a time. So you put more of this catalyst, it takes some time for this reaction to occur. And they're measuring how long it takes that reaction to occur. So like you put in, I don't know, a half a gallon of this catalyst, it'll take a minute, and that's the y value. That's the y value out. The time it takes for this catalyst to occur. And then this is the x value. This is how long it takes the reaction to occur. This time t. So you put in, like, I don't know, one half a gallon, I don't know, or one half of a milliliter, let's say. It's measured in milliliters. It'll take some time. So then this will be a point on the curve, and then I don't know. You put in 1 milliliter. It'll take this long to occur, or maybe shorter. I don't know. Okay, but this is the idea, right? Time is along the y-axis, which is not typical. Typically, time is along the x-axis. But okay, here we have it. Now, we need to know, in this case, this is a good way to, like, for us to understand uh, derivatives. So again, we need to remember, okay, the derivative is the instantaneous rate of change. Okay, so it's the change in the y value over the change in the x value. So in this case, it's a change in time, dt, dA, right? It's how much time has changed, and in this case, time is measured in minutes, so it's a minute. So this is the derivative f prime of a, right? So it's a change in time over the change in x, the change in y over the change in x. And we have it where the time is measured in minutes, so it's minutes over here. And then I have dA, which is measured in milliliters. So I have over milliliters. And this is the units for f prime of a. And now remember, if we're going to differentiate again, we're just going to be differentiating with respect to the other, to the bottom one, to dA again. So it's going to be like dA over dt dA over dA. You're differentiating again, okay? And that's going to be the minutes. And we could say this is said minutes per milliliter, right? You want to find out how much is it that is changing per milliliter, right? So this is minutes per milliliter. You say the slash as a per. So now you could say minutes per milliliter, I should say, per milliliter. Per milliliter. Okay. So it's minutes per milliliter, and that would be this choice right here. And we just have to sort of, like, you could do simpler examples where it's like time is on the x-axis and it makes a little bit more sense, but we can go through that at another time. But right now you guys should just see that it's always that, like, you want to think of it as that you're differentiating with respect to the variable that's gonna, the x variable, right? The x-axis. You're differentiating with respect to x when they write it like this. So along the x-axis here is a, regardless of how many times. If I were to differentiate, if I were to say the third one, if I were to say f triple prime of a, it would literally be minutes per milliliter per milliliter per milliliter, like, and it would just go on down. But that's the idea.